Hi everyone. In this chapter we will be studying linear functions. In this lesson specifically, we will be looking at the slope of a line segment. To begin, let's review the concept of slope.
Okay, so in this lesson we're looking specifically at linear graphs and really specifically about the slope of linear graphs. Now, what is a linear graph? Well, the first line there says it all. It's a line, okay? It's a straight line. Now, when we take a look at these things, you got to notice that there's really not that many options here. Either the line is going to rise to the right or it's going to drop to the right. Okay, now it says here rise to the left here, but I think it's more accurate to say that it drops to the right. Could be a vertical line, could be a horizontal line. So what is it that differentiates these four different types of graphs? And well, the answer is the slope. And we're going to talk about that in just a moment here, but just recognize that on the Cartesian plane, this is essentially what your average line is going to look like. A couple of things that we want to focus on, okay? The intercepts, x-intercept and y-intercept right here, okay? When we cross, where the line crosses the y-intercept, the y-axis, that is the y-intercept. Notice in this point right here that at the y-intercept, x is 0. Okay, now you have to know that. That has to be just something that you are aware of. Okay, that's something you have to memorize here. Same thing was an x-intercept here. This is where y is 0. It's the y-coordinate. Now, in most cases, when I ask for the y-intercept, I simply want the y-coordinate of it. Just like over here, when I ask for the x-intercept, I'm really looking for just the x-coordinate. I already know, okay, when I ask you about the y-intercept, I already know x is 0. And when I ask you for the x-intercept, I already know y is 0. Okay, so just want those other coordinates there, something to be aware of. Now, you really need to be aware of this when we slide over here, because we're going to start to look at equations. Now, we've already seen this show up before, but we're going to be more specific about what it is we're looking at here. We know that this is the equation of a line. Okay, we saw this in the last chapter here when the degree of x and y are both 1. Okay, then we know that we're looking at a linear function. It's going to draw a straight, or a linear function, linear graph here, probably more specific. We already know it's going to have a line as a graph here. We're going to be more specific about the details here. What I want you to understand here is that x and y, okay, every point on this line, okay, has an x and a y, or have x and y coordinates to it. I want you to understand that when we have an equation of a line, when we know that this line represents this graph here, the x and the y that you're seeing here are those x and y coordinates. Now, the reason I state that is because it's kind of assumed at this point that you have made that connection in your heads. But my experience is that a lot of people have not made that connection. That when we look at the equation here and we see this x and y, there's a lot of people that are not making the connection at all to these points along that line right there. I need you to understand that this x and this y are this x and this y. And in fact, it's going to refer to all of them. All of them. All of the infinite different points that exist along this line, when they plug them into this equation, are going to satisfy the equation of that line. Now, it turns out the m and the b here are both constants all the way along this line, but the point can change. We're going to talk more about this particular form here and what these pieces mean in just a bit here. Now, we already mentioned this a little while ago. Let's talk about the slope again. The slope shows how steep a straight line is. Okay, so it's the measure of, and I'll use my pencil here. It's the measure of basically the inclination. Okay, so here's a line, here's a line. What's the difference between them? Well, it's the orientation of that line, right? Okay, flip it over, that sort of thing, and we can use a number to. Well, we can enumerate the value of this orientation. We call that slope. You're going to see in a little while here that we're going to connect that to an angle. Not right away, but in a little while, in a couple chapters here, we're going to associate slope with an angle, and you'll see how you can actually have determine what this angle is. Okay, sort of in essence, the angle of inclination of this thing, as opposed to just the number that we're giving it. So right now, just understand that the larger the slope, okay, the larger the slope, the more inclined it is. Okay, the steeper it is. Okay, The smaller the slope, if you're still talking about positive numbers here, the smaller the slope, the closer you get to zero, the less fun it would be to ski on. That would be boring. That's exciting. Okay, so the larger the number, and the same thing would be if it's negative. Okay, the closer a negative slope is to zero, the less fun it is. The further away it gets, the more fun it is. Okay, now previous to this moment right here, we talked about slope mostly as a rate of change. So if you think back, that's the connection that we're making here. The slope of a line is going to be the rate of change between the independent and dependent variables here. Or think of it like this: it's the rate of change of the dependent variable with respect to a change in the independent variable. And that's what we've got right here. Okay, change of the dependent variable depends on the change of the independent variable. Okay, it looks like this. You would make this delta y over delta x, and that notation is actually really important for later on in the math that you're gonna learn. And we call that rise over run. And you may have already been introduced to this in a science class. That often happens. It's the same idea, exactly the same idea. And so on a line, okay, on a line graph here, if you pick a point, and you can count it up here. Pick 2 points. Maybe this is the better way to describe it. You pick 2 points on the graph, and you're usually going to pick points that are easy to count out here. But then you're going to count up the rise, count out the run, and then the slope is simply going to be the ratio of those two, where the rise is in the numerator, the run is in the denominator. Okay, that's all you got to do. Now, something that you should know is it shouldn't matter which 2 points you pick. Okay, on a line graph. Okay, on a line graph, the slope, or the rate of change, the slope is constant. In fact, that's a really important property. Doesn't matter what 2 points you pick. If I was to have chosen those 2 points right here, this ratio of rise to run will be the same as this ratio of rise to run. Exact same thing. So I want you to be aware of that. That's what makes this equation that we're going to build here, or the equations, I should say, because there are a few of them that we're going to look at. That's what's going to make those things hold true. Now, let's just take a quick look here, and you'll notice that we've already talked about these different examples of the lines here. This is positive slope, okay, where this thing rises to the right. This is negative slope. This one drops to the right. Okay, and the reason I say it like this is, for the most part, okay, often we assume run is positive. Now I'm not writing that in the correct form. I mean, that's not a great sentence here, but we're going to assume the run is always positive. When we scan these things here, we read them left to right. So when I say it rises to the right, okay, drops to the right, the rise is positive, it goes up as we read this left to right. As we read this left to right here. Now, there will be circumstances where you're going to have to go right to left. There's just going to be times when you're plotting a point, and the point that you're given is way over here, and I can't count it out to the right. So you do have the flexibility to do that. Now, what you need to understand by that is simply this. For example, if I give you a ratio of 2/3, you simply need to understand that if I can't go positive with the run, I can go negative, but if I go negative with the run, in this case, I'd have to go negative with the rise as well. Okay, so going two up, 3 over is going to be the same as going 3 to the left, 2 down. Okay, the same sort of thing. You just need to be aware of that. And for example, if you had, like, maybe this was negative 2/3, just be aware that that's the same as 2 divided by negative 3. Negative 2 divided by 3 is the same as 2 divided by negative 3. So whether you treat the run as positive or negative, it shouldn't matter, but you do have to take into account how that affects the numerator. Okay. But once again, just to kind of circle back around here, for the most part, you're going to read the run positive. Over here, there is a bit of a misprint here. This should actually have been 0 over the run, and this will get us a slope of 0. When you got a slope of 0, okay, it's a horizontal line. Okay, horizontal. Now, this doesn't mean that there is no slope. The slope is 0. Okay, there's sometimes a bit of confusion when we talk about things like this and we use the number 0 to represent things. For example, when the graph crosses the y-axis at 0, that doesn't mean that it doesn't cross the y-axis. It means it's going through it at the origin. Okay, that's a common mistake that gets made. And it's the same sort of thing here. When I say 0 slope, I mean we've got a horizontal line. Just like over here, and again, there's a bit of a mistake here. This should have been rise over 0. The slope is undefined when you've got a vertical line. Okay, it's undefined. Now that is the correct answer. Someone's going to say, well, does the slope, is it that the slope doesn't exist? Well, no, you're better off saying it's undefined. Division by 0 is undefined. So when I use the word undefined, we all understand, oh, I know what you're talking about. It caused some division by 0. That's a vertical line. So 0 slope, undefined slope. This is a vertical line. Now, something that's interesting about these two right here, just before we leave them, just a couple things here. Notice that every point on this horizontal line, every point has exactly the same y-coordinate. Every point. It goes through all of the infinite number of different x-coordinates, but the y-coordinate is always the same. In fact, let's say that right here that this is the y-coordinate c here on the y-axis here. The equation of this line would be probably most easily summarized as y equals c, that constant. Okay? So when we define the horizontal line, we're going to define it in terms of the part of it that stays the same regardless of where you look, and that's going to be the y-coordinate. Just like over here, notice that every single one of these points has got the same x-coordinate. Let's say, for example, that that's going through the x-coordinate x equals c. Well, again, the easiest way to define that line is to simply state what is constant forever on that line. So that vertical line can be described as x equals some constant c, just like this horizontal line can be expressed as y equals c. Now, I bring that up because this leads to some confusion. When I say horizontal line, most people associate horizontal with x. However, I use the y to give me the equation. Just like over here, when I talk about a vertical line, most people associate vertical with y, but in this case, to get the equation, I'm going to state what stays the same, and that means talking about x. Just some little things here that you need to pay attention to. Notice that this is a function. This is not a function. In fact, let's run backwards a little bit. Notice that this is a function, and so is this. In fact, the only one that isn't a function is the vertical line. So there is something special about writing the equation of a line in this form. If that is possible, I can write it in that form, or if that's the way I have to write that equation, it suggests that I'm not looking at a function. Okay, which implies that there's going to be a slightly different way of reading that information or pulling the information out of that. Anyway, let's keep going here. So when we're given a graph on a coordinate plane, okay, the easiest thing to do is just to count out the slope, okay? So what we do is we pick 2 points, and like what they've got right here, we've got these 2 points. Now, this isn't perfect. This line segment should have been shifted over slightly here, but you get the idea. So I pick 2 points on there, and I'm hoping to pick 2 lattice points, okay? And so from here to here, I've got this rise. I'm going to count it out. I go 1 block, 2, 3, 4, 5, 6 blocks up, and then 1, 2, 3, 4 over. So 6 over 4. Now, this would not be the best way to write this, and please, please don't leave it like that. Don't leave it like that. When you have an opportunity to simplify, you should always simplify. Notice that both 6 and 4, okay, have a common factor of 2 in there. Now, I'm going to write this out because I've noticed recently that this is not something that people are coming to class comfortable with. 6 is 2 times 3, 4 is 2 times 2. The order when it comes to multiplication and division, the order's a little flexible, okay? I know when we talk about order of operations, it's bed, mass, and so you'd see division before multiplication, but actually the order there is a little flexible. You can do those in either order, so I can actually do the 2 here divided by this 2, and I'm left with 3 over 2 as the simplified form of that. Okay, just like over here, let's take a quick look. So from here, going down, sorry, from this point to this point, now, in this case right here, I'm a little stuck. But this is going to be dropping down 1, 2, 3, 4, 5, 6. But I would say -6. And now in this case right here, I can't avoid the fact that that's really halfway in between. So this is going to be 1, 2, 3, 4, 5.5. Ah, 5.5. Okay, 5.5. 5.5. Well, I really don't like, not an arrow. I want to do an equal sign. I really don't want to use decimals. Decimals aren't awesome. Okay, but I could write this as a fraction, 11 over 5. Okay, because I don't want decimals in a fraction here. And when I talk about the slope, it's more useful to me when I write it as a fraction than it is if I write it as decimals. Because if I write it as a fraction, then I can clearly see the rise versus the run here. But now I've got -6 over 12/5, so I'm going to multiply by the reciprocal. So it's going to be -6 times 5 over 11, which gets me -30 over 11. Now some of you have got to pay attention to this because some of you, I've noticed, want to distribute that 6 to the numerator and denominator here, and that's just not the way fractions get multiplied. Okay, this is like 6 over 1, and then you multiply the numerators, you multiply the denominators. Please watch that. Now, let's do just a couple of examples here, just some more here. We're going to find the slope of each line segment. First of all, before I do this, I notice that this is going to be positive, and I notice, for example, that this one's going to be negative. Okay, this one's positive, this one's going to be negative. I can see that just by looking at it. Here's my the 2 points that they've kind of encouraged me to pick, so I'm just going to count it out. First of all, what's my rise? 1 block, 2, 3, 4, 5, 6. So it's a rise of 6 units over a run of, now this is kind of big, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6 over 10. Now, again, I don't want to leave it like that. I want to simplify this. So 6 over 10, both of those numbers are even, so there's a common factor of 2 there. And when I divide out the 2 over the 2, I'm left with, whoops, sorry, I'm not left with 2. 2 is the number I'm dividing out. I'm left with 3 over 5. That's the slope of this line, positive 3 over 5. Good. Here, let's count that out. The rise is going to be negative. I'm dropping as I go to the right, so I'm dropping 1, 2, 3. So that's -3. The negative is important here. And then the run is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I like that because -3/9, that's easy. It's -1/3. Okay? And notice that how I've written it here is I've written it as -1 over 3, which is the same as -1/3. You treat that whole object, the 1/3 first, and then make the whole thing negative, which, by the way, is exactly the same as 1 over -3. It's just that you're not often going to look at it in this form. More often than not, you're going to look at it as either -1 over 3 or -1 over 3. Okay, so you can count it out. Or you can take a little bit of a shortcut here and use a formula. And the way the formula works is essentially the same as counting it out. It's just that we're taking advantage of a little relationship between those numbers here. So what I'm looking for here, when I counted this out here, I was looking for the difference between these. For example, when I counted out the rise here, I'm essentially looking at this. This line goes through the bottom point here. This line goes through the top point. I'm looking for the difference between them. Okay, the difference between them. And that means subtraction. So I take the one y coordinate, subtract the other. Same thing here. Horizontally, okay, this is where I'm starting, and then I go over here. This is where I end. I simply want the difference between those two lines, okay, just to get that run there. And I do that by writing this out as y2 minus y1. Actually, we should probably zoom in a little bit on that. y2 minus y1 over x2 minus x1. Okay, notice, first of all, that the dependent variable is on top. The independent variable is on the bottom. And notice that we have 0.2 first, 0.1 second. I've recently seen people that switch these. Like they'll start with 0.2 and then they flip them. And if you do that, you're going to get the wrong final answer. Okay, you just need to be consistent. Now, it doesn't even matter which point you choose to be the second point or the first point, as long as you're consistent. These two values here, or these two coordinates, come from one point. These two come from another point. Okay, and so just to illustrate how that works, let's take a look at this next example here. It says determine the slope of the line that passes through, okay, -5, -3, and 2, 1. Okay, well, my slope in this case here is going to be 0.2, again, y2 minus y1. I don't know which one's 2 or 1. I'm just going to decide. Let's maybe make d2 c1. So this is going to be, let's say, yd minus yc over xd minus xc. Okay? So I'm just going to read those off here. So it's going to be 1 minus -3. Oh, right there. That's going to cause problems. 2 minus -5. Okay, look, I tell you what, the powers that be, the ones that have given us the curriculum, they know that if we plug a negative in here, it's going to cause problems. So just be aware that that's the case. They are pretty sure that if they start throwing negative numbers in here, that a lot of students are going to do this wrong, and they are correct. I really need you to just take a moment when you see those negatives and make sure you're doing this correctly. 1 minus -3 is the same as 1 plus 3, or 4. 2 minus -5 is the same as 2 plus 5, so this is 7. That can't be reduced, and so the slope that we're looking at here is 4/7. Okay, be very, very careful when you're using negatives. Okay, now we're going to look at some more examples. So this question, we're just being asked to find the slope given the information here. And we're starting really, really straightforward here. The rise is 1, the run is -2, so it's going to be 1 over -2. But remember, I don't really like how that looks with the negative in the denominator. So I could do this one of two ways. I could either move that negative up top, or I could move the negative in front. And actually, it might even help if I put brackets around it when I do this, just so that I understand what specifically is being made negative. It's the whole thing. These are all equivalent. These two bottom ones are going to be typically easier to work with. Just saying. Here, slope is rise over run, so 4 over -2. Now, before we start talking about where other places to put that negative, let's just take a quick look here and simplify this first. See, in the previous question, 1/2, that is as simple as that ratio is going to get here. 4 divided by -2, because remember, that's what that line means, divided by 4 divided by -2 is just going to be -2. And so I might write this now as either -2 or, and I know some people prefer to write it like this, like -2 over 1. Doesn't really matter, but you do want to simplify that. For this next one here, slope is equal to rise over run. Okay, this is just a matter of simplifying it. Notice that numerator and denominator are both even, so I can cancel this out the 2's here. I can divide out the 2's. Now, let me show you a mistake that gets made frequently. I'll see people do this. They'll see it like this. Okay, that's 2 over 2 times 5. They'll cancel the 2's, and then they'll simply write 5, because there's a 5 left over. No, that's not true. Where is the 5 here? It's in the denominator. So why would the 5 have automatically popped up to the numerator? Correct answer is, I don't know. And that's right, you don't know, because it wasn't supposed to happen. It should have stayed down there. The 2's will cancel. 2 divided by 2 is 1. That 1 that we're writing stays in the numerator, and it becomes 1 over 5. Just watch that. It's such an easy thing to do, but it's also a very predictable mistake. And I hope you hear what I'm saying here. It's a very predictable mistake, meaning that's the sort of thing that we might do in a multiple choice to give you options, okay, to try to, to give you things that we think you might choose instead of choosing the correct answer. Here, slope is equal to -5 over 0. Well, it doesn't really matter what's up there. As soon as we start dividing by 0, this is undefined. Okay, so what we've got here is a vertical line. All right, now in these questions here, what we're going to do is we're going to find the slope using our slope formula. And I'm going to be really consistent. I'll let that second point that you see here be 0.2, this one be 0.1. So now it's going to be y2 minus y1, watch the fact that there's a negative there, over x2 minus x1. So 5 minus negative 3 is the same as 5 plus 3, or 8. Negative 1 minus 3, negative 1 less 3 is going to be negative 4. And when you simplify that, we're going to get negative 2. So the slope of that line segment there is going to be negative 2. Or negative 2 over 1 if you want to write like that. So maybe we write like this, negative 2 or negative 2 over 1 if you want. Over here, slope is going to equal y2 minus y1. Well, I like that. I like subtracting 0. Over 5 minus negative 5. All right, see, right here. Oh, right here. This is so tempting. There's going to be people that are say, it's 0, undefined. No, it's not. 1 minus 0 is 0. Whoops. Wow, okay. Pretend I didn't say that. If we could all just pretend I didn't say that, that'd be wonderful. 1 minus 0 is 1. See, it's so easy to make these little mistakes. What's 5 minus negative 5? Well, the answer is 10. Okay, so the slope of this line segment here is 1/10. Here, slope, again, is going to be y2 minus y1. Okay, there's the subtracting the negative again. And this time, 5 minus 5. Now, notice in this case, okay, this is going to go to 0 because the two x coordinates are the same. Now, if remember what we said earlier in this lesson here, if the x coordinates are the same, that's a vertical line. And if it's a vertical line, the slope is going to be undefined. Now, in this case, it doesn't really matter that the numerator goes to 6. Division by 0 causes this to be undefined. It's a vertical line. This is the example of a line segment here, the line that connects those two. That would not be a function. Okay? And over here, this last one, y2 minus y1 over 5 minus negative 4. Okay, well, in the numerator, 8 minus 8 is 0. Now, that is telling me or hinting that this is going to be a horizontal line. However, there is a circumstance where that wouldn't work, and that's if the denominator also goes to 0. As soon as the denominator goes to 0, it's undefined. But in this case, 5 minus negative 4 is 5 plus 4, that's 9. In that case, there's no problem here. 0 divided by 9 is simply 0. This is a horizontal line. All right, so in this question here, we're going to come up with the slope, x and y intercepts from the given graphs here. Now, these can be read off these graphs pretty easily. So let's take a quick look at this. Take a look at this line segment here. First of all, let's grab the slope here. Now, I'm pretty lazy here, so what I'm going to do is I'm going to pick the x and the y intercepts to do this. So my y-intercept here, and bear in mind what we're asking for. When I ask for the y-intercept, I only want the y-coordinate of that point, where I hit the y-axis here. So x is 0, y is 2. Let's look at the x-intercept. So I come along the x-axis and I'm hitting that. My graph crosses the x-axis when that x-coordinate is 5. I don't need to say what the y-coordinate is. And now I can tell you something about the slope here. Well, first of all, I know it's going to be negative because I see that it's dropping to the right. Okay, I always read it left to right. And I'm dropping by how much? To go from this point to this point. Dropping 2 for going over 1, 2, 3, 4, 5. So negative 2/5 is my slope. Let's take a look at this one. So let's do this the same way. So first of all, we're going to take a look at the y-intercept. Just got to look at my scale here. So negative 1, negative 2. Okay, so down here, negative 4, it looks like, is the intention here. Again, I only need the y-coordinate. I don't need to say, I don't need to write the point out there. The x-intercept here is going to be positive 2, because I'm crossing the x-axis where x is equal to 2. And now the slope. Well, the slope is positive. I can see that because we're rising as we go to the right. And from that point to that point, I go up 1, 2, 3, 4 for going over 2. So it's going to be positive 4 over 2. And I'll simplify that. 4 divided by 2 is 2. Or I know some of you prefer to see that as 2 over 1, which is totally fine. Okay, but you should see the difference. Like even if you prefer to write it this way, you should recognize that it can be written like that. And this last one here, again, let's take a look at the y-intercept here. Where do I hit the y-axis? Well, when the y-coordinate is 4, that's when I hit the y-axis. Okay, there's no other spot where the y-coordinate is 4. The x-intercept is also 4. Okay, that's where I'm hitting the x-axis. Now, in this case, I know my slope is going to be negative, and then going from this point to this point, and it doesn't matter which points I choose, but those are easy to choose. I'll count it out. Negative 1, 2, 3, 4. Positive run of 1, 2, 3, 4. So this is going to be negative 4 over 4, which is just negative 1. There you go. All right, now in this question, we're forcing you to do a little bit of algebra. So find the value of x if I've got the point A, which is 2, 6, and the point B is x8. So I don't know what the x-coordinate is for this point right here. But I'm being told that the slope of that line segment is 2/5. The slope is 2/5. Now I know that slope is going to be y2 minus y1 over x2 minus x1. So let's write that out. That's going to be 8 minus 6 over x minus 2. And I'm being told that that is 2/5, that slope is 2/5 here. Okay, well, take a look at this. Ignore the fact that I have m equals here. Take a look at this. Well, I can simplify that down. 8 minus 6 is just 2. All right, everybody. Now, there are a couple of ways that you can do this, and I think it would be useful for us to talk about all of this. One way that I could do this, and it's probably the most straightforward way, okay, and I'll break this up here, is to notice that I've got fraction equal to fraction, numerator equals numerator. If that's true, the only way that these can be equal, continue to be equal, is if x minus 2 is equal to 5. Okay, that's the only way. If the numerators are equal, and I'm saying that the whole like I can see that the numerators are equal, I'm being told that the fractions are equal, that forces the denominators to be equal. In which case I can add 2 to both sides to get, whoops, not 2, I can add 2 to both sides to get that x is equal to 7. That's one way of doing this. Another way of doing this is to eliminate the fractions here by taking this 2 over x minus 2 equals 2 over 5. I could multiply both sides by 5, and if I do that, up in this numerator here, I'm going to get 10 over x minus 2 is going to equal, well, if I multiply this numerator denominator by 5, I'm going to put a 5 up here. The 5s will cancel. I'm simply left with 2. Then I could take this 10 over x minus 2 equals 2. I can multiply both sides here by x minus 2. Now, on the left-hand side, when I multiply this through, now remember, when I multiply by x minus 2, I'm multiplying the numerator by x minus 2, not both. And when I plug that into the numerator, I'm going to have an x minus 2 on top, an x minus 2 on the bottom. They'll cancel. I'll be left with 10. And this will be 2. On the right-hand side, there is nothing that I can cancel, so it's 2 times x minus 2. Divide both sides by this coefficient here, this leading coefficient. I'll get 5 is equal to x minus 2. And then I will add that 2 over once again to get, oops, sorry, quite honestly, the dog outside distracted me for a moment. X equals 7. Or, if you want another way to think about this, when you have it as 2 over x minus 2 is equal to 2 over 5, there's an algebraic rule that allows us to do this. If you multiply this numerator by this denominator, the result is the same as multiplying this numerator by this denominator. Okay, I mean, some teachers call that cross-multiplying there, but yeah, that maintains equality. That, okay, if I've got a proportion, and it has to be a proportion, fraction equal to fraction. If it's not that, you can't do what I just did here. But here I've got it. I've got fraction equivalent to fraction. So I'm going to multiply this numerator by this denominator, and that will be equal to this numerator times this denominator. And notice that's exactly the same as this line right here. So eventually this becomes x equals 7 once again. Okay, a few different ways to think your way through that problem. Now this question 5 here is very similar to question 4, except the variable shows up a little bit more often. We're going to do the same thing. Now we've got the 2 points, negative 2, 3b, and b comma 4, and they have a slope of 1/3. So now we have to figure out the coordinates of a and b. So our slope, and I'll use this b as the second point, will be 4 minus 3b, y2 minus y1, over x2, b, minus x1, minus negative 2, and this is supposed to equal 1/3. Now, I simplify this a little bit. 4 minus 3b over b plus 2 is equal to 1/3. Okay, well, this is a little bit harder just to make the numerator and denominator equivalent. The reason for that is it may end up being that the simplest way to solve 4 minus 3b equals 1 may give me a value of b that actually doesn't work in the denominator, not the simplest form here. So it's not as straightforward as just setting the numerator equal and the denominator equal. So the easier thing to do here would be to do a little bit of that cross multiplying here. Since it's fraction equal to fraction, I know that the numerator times the denominator, so 1 times b plus 2, is going to equal the numerator times the denominator. Is going to equal 3 times 4 minus 3b. This statement should be equal if this one's equal. Now I'm going to distribute that 3 through, so I've got b plus 2 is going to equal 12 minus 9b. Okay, just distribute that 3 to both of the terms that it's multiplied by. Now what I'll do is I'm going to bring that 9b term over to the left-hand side. I'll add it to both sides. Now there is already a b here, so it's going to leave me with 10 b's there. And at the same time, I'll subtract that 2 to bring that over, and 12 minus 2 is going to be 10. And so I get right away, when I divide there, that b is equal to 1. Now, that tells me that a has got to be the point, whoops, sorry, I don't need to say equals. A is going to be the point negative 2 comma 3. Okay, remember it was 3 times b, and b is 1. B is going to be the point 1 comma 4. There you go. Now, in this question, we're being told to show that these guys are collinear. These 3 points here are collinear. Now, collinear means on the same line. Now, to make that work, to see how this could be possible here, we need to rely on a property of the lines that I was discussing with you earlier here. You need to know that the slope is the same. It's constant all the way through a linear function, okay, or a linear graph here, I should say. So if I find the slope, for example, and I'll use a subscript here, slope of AB, okay, I'll let B be 0.2 and I'll let A be 0.1. So this will be 2 minus negative 3 over 1 minus negative 2. Okay, bearing in mind the negatives in there, got to be careful. 2 minus negative 3 will be 5. 1 minus negative 2 will be 3. There we go. 5/3. Now, that should be the same slope. If they're collinear, that slope should be the same as the slope b to c. Okay, because if the slope is different, then this is what would happen. You'd start at A would go to B, and if the and I'll exaggerate this for a bit. Let's say that the slope is different. There's C. Well, that's what that would look like, and so obviously they're not in a straight line. But if the slope is the same, then we're okay. So this time we'll let C be 0.2. So 7 minus 2, when you compare it to B, over 4 minus 1. 7 minus 2 is 5. 4 minus 1 is 3. Okay, the slopes are the same. Therefore, we know that these guys are collinear. All right, now, I'm glad this is in this lesson. we need to practice graphing. You need to be familiar with this. It's important for you to develop a good sense of what these things look like graphically, so that when we go on and look at more complicated expressions, okay, you can build on this idea. The more comfortable you are with what these things look like algebraically, the easier it will be, for example, to solve equations. So now I'm going to use a ruler for this, but it's not absolutely necessary, as long as I have, when you're doing this, that I can see the points that you're plotting there and you've got a good sense. So you're not doing something really, really bad. Okay, so slope of 2/5 passing through the point -2, 1. Now, -2, 1, bear in mind how this works. I've noticed that there's lots of students out there that don't understand what this means when I go to the graph here. -2, I start horizontally with the independent variable, so -2 is right here, +1 is up here. There's that point. Now, I want the line that I'm about to draw to have a slope of 2/5. Now, I'm going to start here at the given point. Okay, that's my starting point, not at the origin, here. So, starting here, our rise is 2, so I'm going to go up 2, 1, 2, and our run is +5. So 1, 2, 3, 4, 5. Now, I will connect those dots. And there we go. Now, I'm going to put arrows right there. That's not absolutely necessary, but you should be going on beyond these dots, because what we're graphing here are lines. If you do this, and I know that there's a lot of people out there that want to do this, okay, you're only graphing a line segment. Let it go right to the end. And even if you don't put the arrows there, as long as your graph goes to the end of the visible grid, we assume that it carries on beyond that. That's what I want you to graph. Let's take a look at this one. -3, -2 is our point. So starting here, -3, 1, 2, 3 to the left, +2, so here's the point. And then we've got a slope of -2. Okay, now remember, we can write that as, that -2 could be written as -2/1. So that is a rise of -2, so down 2, and a run of 1. Again, I'll pull out the ruler, line them up there. Yeah. And there we go. And here's, for example, this goes right to the end of the, end of the grid, so I assume that that carries on forever from there. Here goes to the point -4, 4. So starting here, we'll come over 4, 1, 2, 1, 2, 3, 4, up 4, 1, 2, 3, 4. And this time we've got a slope of -3/4, so that means we're dropping 3, 1, 2, 3, for a run of 4, 1, 2, 3, 4. See, that takes us right to the y-axis. So I can see right now that the y-intercept of this graph is going to be 1. Didn't ask for that, but I can see that that's going to be the case. And there we go. Oops, sorry, there was there was something underneath the paper that made it wobble there a little bit. Over here, the slope is undefined. Okay, undefined, going through the point -2, 4. Okay, so -2, 4, let's find that point first. 1, 2. 1, 2, 3, 4. If the slope is undefined, that means it's a vertical line. You kind of just need to know that off the top of your head. That's got to be clear. And now once we've got this, it's probably a good idea for us to give a quick indication of what the equation of the line is here. At least this is something I feel we need to practice. Remember that what's happening here along this line is the x-coordinate is constant all the way across here. So in this case here, if I can see one x-coordinate, I know them all. So in this case, x is going to equal -2. That right there, that little equation defines this line. Notice there's no y-intercept. It never gets there. Its x-intercept is -2 because all of the x-coordinates are -2. Okay, similar sort of thing here, and you should almost expect this. As soon as you graph a vertical line, you should probably suspect that we're going to graph a horizontal one. Slope is 0 through 3/4. Sorry, not 3/4. That's terrible. 3, 4. So horizontally, 1, 2, 3. And then 1, 2, 3, 4. And with a slope of 0, we're going horizontally, so it's going to look like this. I'll put arrows there just to indicate, so it's a little bit easier to see. And once again, in this case right here, remember that for a horizontal line, we know that the y coordinates are always the same. So if I know one of the y coordinates, I know all of them. And so that's how I would describe that line. Okay, now lastly here I've got the point that I'm going through is 1, -2, so, sorry, -1, -2. So starting at the origin, -1, so 1 to the left and then 2 down. And I've got a slope of 3. The slope of 3 is, remember, that's just 3 over 1. So it's got a rise of 3, a run of 1. So 1, 2, 3, but over 1. And then again, I will connect those points. And there we go. Okay, I hope that makes sense. I hope you feel confident with that. I hope that makes sense. So, because we really do need you to be able to do this. I've noticed that frequently when we get to Math 20, there are times that we need to refer back to equations of lines, and I have all sorts of. It's been the case frequently where students just have forgotten this. I really want you to remember what's going on here. This is a really important idea in Math 10. Okay, determine the slope of the diagram. Now, it's kind of difficult to understand what exactly they're talking about here, what specifically they're referring to, but they are referring to like this line segment right here. This could, for example, represent like a joist in a roof, right? The rafters. So what's the slope of that line here? Well, notice from here to here, the slope of this line, it's got a rise of 5. And a run of, well, it's not 24. 24 would put us out to here. That's a run of 12. Just like for this line segment right here, to go from here to here, remember, this is 5 up, and we're assuming this is going down to 0. So this has had a drop of 5 for a run, once again, of 12. Now, most of the time that you're asked this question, because this sort of question does show up on exams, usually what we're referring to is this. We just want you to see essentially that you got to take half of that base there, right? Normally when people are talking about, like if they're talking about rafters or whatever, you're talking about the slope of the line. Normally we won't refer to the negative part. We just understood that it's symmetrical. Okay, and so they'll typically just use the 5/12.